Hello everyone. In this session, we are going to discuss about atom models or atomic theories. Atom models or atomic theories from the chapter Atomic Physics. Chapter name Atomic Physics. The topic name is atom models. Atom models or atomic theories. Atomic theories, right? What is meant by atom models? Atom models are nothing but the suggestions given by many physicians or philosophers regarding an atom are called atom models or atomic theories. Okay, the suggestions are given by many physicians and philosophers regarding an atom are called atomic theories or atom models, right? What is meant by atom? Okay, you know very well about that. Atom is nothing but the smallest particle of an element. Smallest particle of an element. It was discovered by John Dalton. The concept of an atom were proposed by two Greek philosophers, Leucippus and Democritus. Okay, Leucippus. And Democritus. Okay, who are Greek philosopher. Okay, proposed about the concept of an atom around 400 BC, right? Later, many atom models were proposed at different times. They are, first one, Dalton's atom model. And second, J.J. Thomson atom model. Next, Rutherford's atom model. And fourth, Bohr's atom model. Next, Sommerfeld's atom model. And last one, Vector atom model. So these are different atom models proposed by many or different physicians or philosophers regarding an atom, right? The first atom model was proposed by John Dalton. So that is why it is called Dalton's atom model or John Dalton's atom model, right? According to John Dalton, an atom is nothing but a smallest particle of an element. Right? The atom can neither be created nor be destroyed. The atom cannot be created, cannot be destroyed, right? And the atoms of same substances are identical. That is, the atoms in the chalk piece are identical. Okay, but the atoms of other substances are different. The atoms of same substances are identical, but it differ from other substances. It means the atoms in the chalk piece are identical. When we compare it to the atoms in the blackboard, the atoms are different. Okay, the atoms in the blackboard and the atoms in the chalk piece are different. But the atoms in the chalk piece alone are identical, right? And the atoms retain their individuality in all types of a chemical combination. Right? We know one familiar chemical equation, that is NaOH plus HCl that gives NaCl plus H2O. In chemistry, this is very familiar chemical equation, right? So in this equation, before a reaction, after reaction, for example, sodium atom, okay, is always retain its individuality, okay? So before a reaction, before the sodium atom is reacts with hydrochloric acid, and after sodium chloride is react combined with the water, the sodium retain its individuality. Its individuality means its behavior does not change during the chemical reaction. So these are the suggestions given by John Dalton in his atom model, right? So according to John Dalton, atom or the smallest particle of an element, the atoms can neither be created nor be destroyed. The atoms of same substances are identical, but it differ from other substances. The atoms retain their individuality in all types of chemical combination. So these are the suggestions given by John Dalton, right? So next atom model, J.J. Thomson's atom model. Right? In this atom model, the atoms are visualized as, or considered as, or assumed as homogeneous spheres, right, which contain uniform distribution of positively charged particles, or positive charges, right? So according to J.J. Thomson, in his atom model, the atoms are a sphere of a radius or a diameter is of the order of 10 power minus 10 meter, right, which containing positive charges. The positive charges in the sphere is uniformly distributed over the sphere, and the negatively charged particle, that is the electrons, are embedded in the positively charged sphere like this. Right? So according to J.J. Thomson, the atoms are a sphere of diameter 10 power minus 10 meter, which is containing positive charges, which is spread out over the sphere, and the negative charges in the atom are embedded in the positively charged sphere, like seeds in watermelon. So that is why the J.J. Thomson's atom model is also called watermelon model. Or otherwise called the plum pudding model. So the atoms are assumed to be a homogeneous sphere which containing uniform distribution of a positively charged particle, in which the negatively charged particle, that is the electron, are embedded in it, right? Which is like the seeds in watermelon. So that is why the J.J. Thomson's atom model is also called watermelon model. And it is also called the plum pudding model, right? And according to Thomson, an atom is electrically neutral. Okay, why? Because the atom contain equal amount of positive charges and equal amount of negative charges carried by an electrons. That is, the total amount of positive charges in an atom is equal to the total amount of negative charges carried by an electron in the same atom. So an atom is electrically neutral. Atom is electrically neutral because the total amount of positive charge is equal to the total amount of negative charge. So the net charge of an atom is 0. So an atom is electrically neutral. Reason, the total amount of a positive charge is equal to the total amount of negative charges carried by an electron. So the net amount of a charge in an atom is 0. So that is why an atom is electrically neutral. So this was suggested by J.J. Thomson. Right. Next, and this atom model fails to explain the stability of the atom. J.J. Thomson's atom model fails. Why? Okay, it does not explain the stability of an atom. Stability of an atom. Because according to J.J. Thomson, the charges in an atom is always at rest. The charges in an atom is always at rest. They are always stationary. So, an atom is always stable. Atoms are stable. So, atoms are stable. Okay, reason? The charges in an atoms are at rest. They are always stationary. So, the atoms are highly stable. Highly stable. So, this was suggested by Thomson, J.J. Thomson in his atom model. But according to classical electrodynamics, the atoms cannot be stable. The atoms cannot be stable because no stable equilibrium points exist in electrostatic configuration. No stable equilibrium exists or no stable equilibrium points exist in electrostatic configuration, which is known as Earnshaw's theorem. Earnshaw's theorem. Earnshaw's theorem. What is Earnshaw's theorem? No stable equilibrium points exist in electrostatic configuration. Electrostatic configuration. So the atoms cannot be stable. Atoms cannot be stable according to classical electrodynamics. But according to J.J. Thomson, atoms are highly stable because the charges in the atom is always at rest. The charges in an atom is always stationary. So atoms are stable. But according to classical electrodynamics, the atoms cannot be stable. Cannot be stable, right? And another one drawback is there in J.J. Thomson's atom model. That is, this atom model could not explain the origin of spectral lines observed. The origin of spectral lines observed in the spectrum of hydrogen atom and hydrogen-like atom. Hydrogen-like atom. So J.J. Thomson's atom model could not explain about the origin of spectral lines observed in the spectrum of hydrogen atom and hydrogen-like atoms. So these two are main drawbacks in the J.J. Thomson's atom model, right? So once again I repeat, according to J.J. Thomson, the atoms are visualized as a homogeneous sphere, which containing a uniform distribution of positively charged particles, right? And the negatively charged particles, that is electrons, are embedded in it, which is like seeds in watermelon. So the J.J. Thomson's atom model is also called watermelon model or plum pudding model. And according to Thomson, an atom is electrically neutral. Okay, why? It contains equal amount of positive charges and negative charge. So the net charge value is 0. So an atom is electrically neutral, right? But according to J.J. Thomson, atom is highly stable. Reason, the charges in the atom is always stationary. But according to classical electrodynamics, atoms cannot be stable. Atoms cannot be stable. Okay, so reason, according to Earnshaw's theorem, no stable equilibrium points exist in electrostatic configuration, right? And another one drawback in the J.J. Thomson atom model is that this atom model could not explain the origin of spectral lines. Origin of spectral lines observed in the spectrum of hydrogen atom and hydrogen-like atoms. So later we will discuss about that, right? Next we go for Rutherford's atom model. Right. So Rutherford proposed his atom model based on the results of scattering of alpha particle experiment. Conducted by his students Geiger and Marsden. So Geiger and Marsden, who are the student of Rutherford, they were conducted a simple experiment. That is, the scattering of alpha particle by using a thin gold foil. In order to investigate the structure of an atom. Okay, to investigate structure of an atom, Geiger and Marsden, who are Rutherford's student conducted a scattering, alpha particle scattering experiment. Alpha particle scattering experiment based on Rutherford's idea. Based on Rutherford idea, okay, in order to investigate structure of an atom. Okay, so the results obtained from alpha particle scattering experiment are summarized as Rutherford's atom model. Rutherford's atom model. So Rutherford's atom model is full and full. The results obtained from scattering of alpha particle experiment, which is conducted by Geiger and Marsden. Geiger and Marsden. Right. Now we go for the experimental arrangement of the scattering of alpha particle by a thin gold foil. Right. The experimental arrangement consists of a lead box. Right. This is lead box or lead black. Lead block. Right. In which a source of alpha particles are polonium, radium and radon. So these are some examples of source of alpha particle. Right. First, what is alpha particle? Alpha particles are nothing but helium nuclei. Alpha particles are nothing but helium nuclei, right? And alpha particles are positively charged particle. Alpha particles are positively charged particle, right? Whose charge is equal to, that is, the charge of alpha particle is equal to 2 times of a charge of an electron. The charge of alpha particle is 2 times of a charge of an electron, right? And mass of alpha particle is 4 times of a mass of a proton. The mass of alpha particle is equal to 4 times of a mass of proton, whose charge is equal to 2 times of a charge of an electron. 2 times of a charge of an electron. Alpha particles are positively charged particle. Alpha particles are nothing but helium nuclei. Geiger and Marsden conduct a simple experimental arrangement, and in which they were used alpha particle to scatter by using a thin gold foil. For the purpose of investigate structure of an atom. Okay, based on Rutherford's idea. Right? So this is, experimental arrangement of alpha particle scattering experiment. The experimental arrangement consists of a lead block in which a source of alpha particle is placed like this. Suppose polonium. So polonium sample is placed inside the lead block, okay, which is acts as a source of alpha particle. Right. So this alpha particle comes out from the lead box through a fine hole which is made in the lead box. So this is a fine hole is made in the lead block through which the alpha particle comes out from the lead block. Right. So there is a lead block in which a polonium sample is placed, which acts as a source of alpha particle. The alpha particle comes out from the block through this fine hole, right? And then this alpha particle is made to pass through a small gap in the lead screen. So this is a lead screen. Right, this alpha particle is passed through the fine gap in the lead screen. Right, this is alpha particle. Right. Finally, this alpha particle is made to strike on a thin gold foil. So this is gold foil. Thin gold foil. Right. So this is lead block. A small hole is made in this lead block, through which the alpha particle comes out from the sample through this hole, and then it is made to pass through a fine gap in the lead screen. Finally, it is allowed to fall on a thin gold foil. Allowed to fall on a thin gold foil, right? So it was observed that when the alpha particle is strikes on the gold foil, it is scattered in different angles. It is scattered at a different angle. It is scattered at different angles. Scattered at a different angle. Right? Suppose here theta is called scattering angle. Scattering angle. So when the alpha particle strikes on gold foil, it is scattered at different angles. Right? Suppose here theta be the scattering angle. Right? So behind the gold foil, there is a fluorescent, movable fluorescent screen. Movable fluorescent screen, which is coated with zinc sulfide. Is placed behind the gold foil. Okay, in order to collect the alpha particle, to catch the alpha particle, there is a fluorescent movable screen is placed behind the gold foil. Right? So which is coated with the zinc sulfide. This is one of the fluorescent material. Okay, by using this screen, we can, the fluorescent screen can be moved from 0 degree to 180 degree. Okay, the screen can be moved from 0 degree to 180 degree. So that is what is called movable fluorescent screen. Why it is called a fluorescent screen? Because the screen is coated with zinc sulfide. So zinc sulfide is one of the fluorescent material, right? So whenever the alpha particle is strikes on the screen, a tiny flashlight is produced on it. Okay, when the alpha particle strikes the screen, tiny flashlights are produced or tiny flashlights are absorbed, right? It can be seen by using low power microscope. Okay, the tiny flashes light absorbed on the fluorescent screen can be seen with the help of a microscope, and this arrangement can be rotated from 0 degree to 180 degree. So that is why it is called movable fluorescent screen, which is kept behind the gold foil. Whenever the alpha particle strikes the gold foil, it is scattered in all possible directions. It is scattered at different angles, right? That the tiny flashlight is produced when the alpha particle strikes on it, right? It can be seen with the help of a microscope. So this is experimental arrangement of the scattering of alpha particle by a thin gold foil. This experiment is conducted by two scientists, namely Geiger and Marsden, who are the students of Rutherford. Based on his idea, they were conducted this experiment. Okay, for what purpose? To investigate the structure of an atom. Right? The results attained from this experiment are summarized as Rutherford's atom model. Right? From alpha particle scattering experiment, a few observations. Some observations are made. Okay, they are: first one, most of the alpha particles are passes through the gold foil without any deviation. Right? When the alpha particle strikes on the gold foil, most of the alpha particle is passed through the gold foil without any deviation. This is first thing. Second one, some alpha particles are scattered through smaller angles. Okay, some alpha particles are scattered through smaller angles. Right? Second, and third one, few alpha particles are scattered through large angles. Right? And the fourth one, very few alpha particles are scattered back. That is scattered back by 180 degree. That is, the alpha particles are turned back in the same path. Right? So these are some observations made from alpha particle scattering experiment. So what are the observations made from alpha particle scattering experiment? First one, most of the alpha particles are passed through the gold foil without any deviation. Okay, they travels in straight lines. And the second one like this. Okay, actually Rutherford expected that all the alpha particle passed through the gold foil without any deviation. But the result observed from alpha particle scattering experiment is that most of the alpha particle passed through the gold foil without any deviation. And some alpha particles are scattered through smaller angles. And few alpha particles are scattered through large angle. Okay, large angle. This is greater than 90 degree. Okay, this is almost equal to 180 degree. This is exactly equal to 180 degree. Right? So most of the alpha particle passed through the gold foil without any deviation, and some alpha particles are scattered through smaller angle, that is less than 90 degree. Less than 90 degree. And few alpha particles are scattered with the large angles. Large angle, that is greater than 90 degree. Greater than 90 degree. And very few alpha particles are scattered back by 180 degree. So these are some observations made from alpha particle scattering experiment, right? And one more thing, it was experimentally observed that the scattering angle is increases, the number of scattered alpha particle becomes decreases. That means the number of alpha particle, scattered alpha particle is inversely proportional to scattering angle. Is inversely proportional to scattering angle. That means if the scattering angle is increases, the number of scattered particle becomes decreases. Number of scattered particle become decreases. If the microscope is kept exactly along the axis of the gold foil, we can see the more intensity of the flash light produced on the movable fluorescent screen. Movable fluorescent screen. If the scattering angle is gradually decreases, the intensity of the light produced on the fluorescent screen becomes decreases. It means the number of alpha particle strikes on the screen becomes decreases. Right? So this is a graph drawn between the scattering angle and the number of scattered alpha particle. From this graph, it is clear that if the scattering the scattering angle is increases, the number of scattered alpha particle observed becomes decreases. So that is why we can get a graph like this. The graph is like a rectangular hyperbola. Why? Because n is inversely proportional to theta. Here n is the number of scattered alpha particle observed with the help of movable fluorescent screen, and theta is scattering angle. So as the scattering angle increases, the number of scattered alpha particle decreases. Right? The observation made from alpha particle scattering experiments are: first one, most of the alpha particle passed through the gold foil without any deviation. Second, some alpha particles are scattered through smaller angle, that is less than 90 degree. And few alpha particles are scattered through large angle, that is greater than 90 degree. And very few alpha particles are deflected back by 180 degree. So these are some observations made from alpha particle scattering experiment. Right. So from this observation, Rutherford concluded that most of the space inside the atom is empty. That is, the atom has lot of empty space. So this is one of the conclusion given by Rutherford from this experiment. Right? What is the conclusion? Most of the space inside the atom is empty. Right? And the second one, there is a small central core of an atom which consists of the entire positive charge of the atom, which is called nucleus. There is a small central core of an atom, which is called nucleus, where the total amount of positive charges is concentrated in this region. And also the whole mass of the atom is also concentrated in this region. The name of the region is called nucleus. Right? A nucleus. So this is another conclusion given by Rutherford after performing this experiment. Right? So first conclusion, most of the space inside the atom is empty. Second, the whole positive charge of the atom, the entire mass of an atom is concentrated in tiny central core called nucleus. Right? And the electrons in an atom is revolve around the nucleus in circular orbit. Right? But according to J.J. Thomson, The negatively charged electron in an atom is always stationary. They are always at rest. Okay, that is it maintaining a static equilibrium. Static equilibrium. But according to Rutherford, the electrons in an atom are not stationary. They are revolve around the nucleus in circular orbit. Circular orbit. Right. So these are some conclusions made by or given by Rutherford from alpha particle scattering experiments. So what are the conclusion? First one, atom has a lot of empty space. Second, the whole positive charge of an atom and the entire mass of an atom is concentrated in tiny central core called nucleus. And the third one, the electrons in an atom revolve around the nucleus in circular orbit. So these are some conclusion made by Rutherford from alpha particle scattering experiment. Right. Suppose an alpha particle is directed towards the center of the nucleus of a gold nucleus. Right. When the alpha particle is directed towards the center of the nucleus, it will move at one particular distance and stop at a particular point. Okay, and it stops momentarily and then it returns back to its original path. Right? When the alpha particle is directed towards the center of the nucleus, it will move up to a particular point and it takes some rest in this point and then it returns back. Right. The minimum distance between the center of the nucleus and the point where the alpha particle take rest momentarily and returns back to its original path is called the distance of closest approach. It is denoted by R0. Distance of closest approach. Distance of closest approach. So whenever the alpha particle is directed towards the center of the nucleus, it will move at, up to a distance R0 where the entire kinetic energy of the alpha particle becomes converted into electrostatic potential energy. That minimum distance between the center of the nucleus and this point is called distance of closest approach. The distance of closest approach is denoted by R0. Right. Suppose let m be the mass of the alpha particle. Suppose it is moving with a velocity of v0. Right. Then the kinetic energy of the alpha particle is given by of m v0 square. Okay. Here the alpha particle is moving with a velocity v0 and its mass is m. Then the kinetic energy possessed by the alpha particle is given by of m v0 square. When the alpha particle reaches at the distance of a closest approach, this entire kinetic energy of the alpha particle becomes converted into electrostatic potential energy. Okay, so that is the kinetic energy of the alpha particle is equal to electrostatic potential energy. Okay, we know that electrostatic potential energy is given by the expression U is equal to Q1 Q2 divided by 4 pi epsilon naught R. U is equal to Q1 Q2 divided by 4 pi epsilon naught R. If two charges, one of them is Q1 and another one is Q2, separated by a distance of R, then there is a electrostatic potential energy exists between these two charges. The electrostatic potential energy between these two charges can be calculated by using this formula. U is equal to Q1 Q2 divided by 4 pi epsilon naught R. Right? Q1, one of the magnitude of the charged particle, and Q2, the charge of another particle, and R, the distance between the two charged particle. If the charges is placed in air medium, then the electrostatic potential energy between these two charges is given by U is equal to Q1 Q2 divided by 4 pi epsilon naught R. Right. Here, one of the charge, that is Q1, is alpha particle. Suppose alpha particle. So Q1 is given by 2e. Already I told the charge of alpha particle is 2 times of a charge of an electron. 2 times of a charge of an electron. So Q1 is taken as 2e, right? And another charge is nucleus, right? Actually, the atom is electrically neutral. Reason, the atom consists of equal amount of positive charges and negative charges. The positive charge is completely concentrated in the nucleus, right? So the charge of the alpha particle is 2e, and the charge of the nucleus here Q2, which is equal to Ze. The general equation for charge of nucleus is Ze, where Z atomic number of the nucleus, and E charge of an electron. Here 2e charge of alpha particle, Ze charge of gold nucleus. Here Z atomic number of gold nucleus, right? So what is the distance between alpha particle and the nucleus? That is R0. Then the electrostatic potential energy between these two is given by U suffix E is equal to 2e into Ze divided by 4 pi epsilon naught into R0. 2e Ze divided by 4 pi epsilon naught R0, or 2 Z E into E square divided by 4 pi epsilon naught R0. This is electrostatic potential energy between alpha particle and gold nucleus. When the alpha particle reaches in this point, the kinetic energy of the alpha particle is completely converted into electrostatic potential energy. Right? So electrostatic potential energy between the alpha particle and gold nucleus is given by 2 Z E square divided by 4 pi epsilon naught R0, where R0 the distance of closest approach. Right? So at the distance of closest approach, kinetic energy of the alpha particle is equal to electrostatic potential energy. Right? Substitute kinetic energy equation and electrostatic potential energy equation here of m v naught square equal to 2 Z E square divided by 4 pi epsilon naught R0. Right? Therefore, R0 is equal to 2 Z E square divided by 4 pi epsilon naught into of m v naught square. What is of m v naught square? This is kinetic energy of the alpha particle. Suppose kinetic energy of the alpha particle is taken as Ek. Right? For our convenience, of m v naught square can be taken as Ek. Then this equation becomes R0 is equal to 2 Z E square divided by 4 pi epsilon naught into Ek. So this equation gives the distance of closest approach of alpha particle. The distance of closest approach is given by the formula R0 is equal to 2 Z E square divided by 4 pi epsilon naught Ek. Z atomic number of the given nucleus, right? And E charge of an electron. Epsilon naught permittivity of free space. Okay, what is the value of permittivity of free space? 8.854 into 10 power minus 12 Coulomb square Newton inverse meter power minus 2. Okay, or 1 by 4 pi epsilon naught value 9 into 10 power plus 9. 1 by 4 pi epsilon naught value 9 into 10 power plus 9. Right? What is Ek? The kinetic energy of the alpha particle. Right? So Rutherford, by using a different nucleus, he calculated the distance of closest approach value. The distance of closest approach value lies in between 10 power minus 14 meter to 10 power minus 15 meter. Okay, so Rutherford tried to measure the radius of the nucleus or diameter of the nucleus by using this formula, right? But actually the diameter and the radius of the nucleus is always less than the distance of closest approach. For that, he conducted several experiments by using different nucleus, and he calculated the distance of closest approach value by using this formula. He get that value from 10 power minus 14 meter to 10 power minus 15 meter. It means the diameter of the nucleus, it is of the order of 10 power minus 15 meter to 10 power minus 14 meter to 10 power minus 15 meter, right? So this is for about distance of a closest approach. And the alpha particle is directed towards the center of the nucleus of the gold atom. It reaches at one particular point and take rest momentarily. After that, it returns back to its original path. Here, the distance between the center of the nucleus and where the alpha particle take rest momentarily and returns back to its original path, that distance, minimum distance is called distance of closest approach. Distance of closest approach, right? What happened at the distance of closest approach? The kinetic energy of the alpha particle is completely converted into electrostatic potential energy. Kinetic energy of the alpha particle is, suppose Ek is equal to half m into V naught square. What is m? Mass of the alpha particle, and V naught, velocity of the moving alpha particle. Velocity of the moving alpha particle. So kinetic energy of the moving alpha particle of m V naught square. When the alpha particle reaches in this point, okay, this kinetic energy becomes converted into electrostatic potential energy. Electrostatic potential energy of alpha particle and this nucleus is given by U suffix E is equal to 2Z E square divided by 4 pi epsilon R naught, where R naught distance of closest approach, right? And in this point, the kinetic energy is converted into electrostatic potential energy. That is K is equal to UE, right? Kinetic energy of m V naught square, electrostatic potential energy 2Z E square divided by 4 pi epsilon R naught. We need distance of closest approach. So take this side. Then this equation becomes R naught is equal to 2Z E square divided by 4 pi epsilon naught into half m into V naught square. Instead of half m V naught square, we can write Ek. So the distance of closest approach formula becomes R naught is equal to 2Z E square divided by 4 pi epsilon naught Ek. So this is an expression for the distance of closest approach, right? So Rutherford calculated the distance of closest approach value by using different nucleus. Okay, he get the distance of closest approach value is from 10 power minus 14 meter to 10 power minus 15 meter. Okay, the distance of closest approach is equal to, it never equal to the radius of the nucleus or diameter of the nucleus. Dear students, so far we discussed about J.J. Thomson's atom model and scattering of alpha particle by a thin gold foil experiment, and next distance of closest approach. Am I right? Right. So according to J.J. Thomson, the atoms are assumed to be homogeneous spheres which containing uniformly distribution of positively charged particle, right, in which the negatively charged particles are embedded in it, right, like the seeds in watermelon. So that is why J.J. Thomson's atom model is also called watermelon model or plum pudding model. Right? And also Thomson was suggested that an atoms are electrically neutral, right? Why? Because it contains equal amount of positive charges and negatively charges. So the net charge of the atom is 0. So that is why an atoms are electrically neutral, right? And also he was suggested that the charges in the atom are always at rest. Okay, Thomson was suggested that the electric charges in the atom are always at rest, right? And another one drawback is there in the J.J. Thomson's atom model, that is, this atom model could not explain the origin of spectral lines observed in the spectrum of hydrogen atom and hydrogen-like atoms. So this is what about J.J. Thomson's atom model, right? And scattering of alpha particle by a thin gold foil experiment was conducted by Geiger and Marsden, right? Based on Rutherford's idea, right? After performing that experiment, some conclusions and observations are made. So what are the observations made from alpha particle scattering experiment? Right, the first one, most of the alpha particles are passed through the gold foil without any deviation. Second, and some alpha particles are scattered through smaller angle, that is less than 90 degree. And few alpha particles are deflected through larger angle, that is greater than 90 degree. and very few alpha particles are reflected back to its original path. That is, it deflected through 180 degree. So these are some observations made from alpha particle scattering experiment performed by Geiger and Marsden. Right. And what are the conclusions were made from alpha particle scattering experiment? First one, most of the space inside the atom is empty. Okay, the atom has a lot of empty space. Atom has a lot of empty space, and there is a small central core of an atom which is called the nucleus, where the entire positive charge and the whole mass of the atom is concentrated in it. Right, that is the central core of an atom is called nucleus. Right, and next the electrons are revolve around the nucleus in circular orbit. The electrons are revolve around the nucleus in circular orbit. So these are the conclusions given by Rutherford after performing alpha particle scattering experiment. Right? Okay. And next, distance of a closest approach. What is meant by distance of a closest approach? The minimum distance between the center of the nucleus and the alpha particle just before it get reflected through an angle of 180 degree. Through an angle of 180 degree. Right. The distance of closest approach is given by the formula. The distance of closest approach is given by R0 is equal to 2Z E square divided by 4 pi epsilon naught Ek. The distance of closest approach is given by R0 is equal to 2Z E square divided by 4 pi epsilon naught Ek. What is Z? Atomic number of the gold nucleus, and E charge of an electron, epsilon naught permittivity of a free space, and Ek the kinetic energy of the alpha particle. Kinetic energy of the alpha particle. Right. Okay. This is an expression for the distance of a closest approach. Right. Okay. So Rutherford performed different experiments by using a different nucleus. And he was calculated the distance of a closest approach for the different nucleus. The values are lies in between 10 power minus 14 meter to 10 power minus 15 meter. Okay, so in order to determine the diameter of the nucleus, Rutherford performed large number of experiments by using different nucleus, and he also found that the distance of closest approach value is lies in between or varies in between 10 power minus 14 meter to 10 power minus 15 meter. So from which he was concluded that the diameter or the radius of the nucleus is of the order of 10 power minus 14 meter or 10 power minus 15 meter. Right? So distance of closest approach is given by R0 is equal to 2Z E square divided by 4 pi epsilon naught Ek. Right? And also he was suggested that if the scattering angle is increases, the number of alpha particle, scattering alpha particle becomes decreases. As the scattering angle is increases, the number of alpha particles, scattered alpha particle becomes decreases. Right? So these are the conclusion given by Rutherford from alpha particle scattering experiment. And distance of closest approach is given by this formula. Right? And the distance of closest approach value is lies in between 10 power minus 14 meter to 10 power minus 15 meter. Right? Okay, next we go for impact parameter. Impact parameter. What is meant by impact parameter? Okay, this is simple. Right? When the alpha particle is directed or moves towards the gold nucleus, at a very large distance, it gets deflected through a small angle. Right? Already I told, if the distance of the alpha particle from the center of the nucleus is increases, the scattering angle becomes decreases. Here the alpha particle is moves towards the gold nucleus at a large distance. So the scattering angle value is less. So what is theta? Scattering angle. Actually, alpha particle is moving in this direction, suppose with a velocity of V0. Right? Due to this nucleus, the alpha particle gets deflected in this direction with an angle of theta. Here theta is called scattering angle. Scattering angle. Why the alpha particle gets deflected through an angle of theta? Because the nucleus is a positive charge and alpha particle also positive charge. So due to electrostatic repulsion, the alpha particle gets deflected from its original path and it is moves with an angle of or deflected through an angle of theta. Right. Now, what is meant by impact parameter? Right. Simple. A perpendicular distance between the center of the gold nucleus and the direction of velocity vector of the alpha particle at a large distance. When it is moves at a large distance. So this is a definition of impact parameter. So here the impact parameter is denoted by B. Okay, once again I repeat, impact parameter is nothing but a perpendicular distance between the center of the nucleus and the direction of velocity vector of the alpha particle. When it is travels at a larger distance. And impact parameter is denoted by B. Here theta, scattering angle. V naught, the velocity of the alpha particle. And this is the direction of velocity of the alpha particle. Okay, due to the electrostatic repulsion, its path changes from this direction to this direction. And it deflected through an angle of theta, that is called scattering angle. Here B is impact parameter, right? And it was experimentally found that there is a relationship between impact parameter and scattering angle. The relation between impact parameter and scattering angle is that B is proportional to cot theta divided by 2. Okay, B is proportional to cot theta divided by 2. If theta value is increases, cot theta value becomes decreases. If cot theta value becomes decreases means automatically impact parameter value also decreases. Or on other hand, if the impact parameter is less, cot theta value also less, but theta value becomes high. It means if the alpha particle approaches the nucleus at a larger distance, the alpha particle gets deflected through a smaller angle. So B is proportional to cot theta divided by 2. This is a relationship between impact parameter and scattering angle. Right. So if you want to remove proportional, we should introduce proportionality constant. So B is equal to K into cot theta divided by 2. Here K is called constant of proportionality or proportionality constant. And proportionality constant K is given by 1 divided by 4 pi epsilon naught 2 Z E square divided by m V naught square. Okay, proportionality constant K is equal to 1 by 4 pi epsilon naught 2 Z E square divided by m V naught square. Here, for a given velocity of alpha particle, this K value is constant. If the velocity of the alpha particle changes, then this K value also changes. So for a given velocity of the alpha particle, here K value is a constant. 1 by 4 pi epsilon naught, this is constant value. And Z, for a gold nucleus, Z value is constant. E charge of an electron, it is also constant. M mass of alpha particle, that value also constant. For a given velocity, K value is a constant. It is given by the relation 1 by 4 pi epsilon naught 2 Z E square divided by m V naught square. Right? Therefore, impact parameter B is equal to 1 divided by 4 pi epsilon naught 2 Z E square divided by m V naught square into cot of theta divided by 2. Right? So this is relation between impact parameter and scattering angle. Right? From this equation, it is clear that if the impact parameter is increases, the scattering angle becomes decreases. Impact parameter is increases, the scattering angle becomes decreases. It means if the alpha particle comes close to the nucleus of the atom, nucleus of the gold, then the scattering angle value becomes increases. If the alpha particle moves away from the gold nucleus, the scattering angle value becomes decreases. That means if B value increases, theta value becomes decreases. If B value decreases, the theta value becomes increases, right? So from this equation it is clear that if the impact parameter is increases, the scattering angle value becomes decreases. If the alpha particle approaches the nucleus at a larger distance, the alpha particle gets deflected through smaller angle, right? Understand? Once again I repeat what is meant by impact parameter. Impact parameter is nothing but a perpendicular distance between the center of the nucleus and the direction of velocity of the alpha particle when it is at a larger distance. When it is at a larger distance. Relation between impact parameter and scattering angle is B is proportional to cot theta divided by 2. Here, if B value decreases, the theta value increases. If B value increases, the theta value decreases. The final relation is B is equal to 1 by 4 pi epsilon naught 2 is at E square divided by m V naught square cot theta divided by 2. Right, already I told based on the results obtained from alpha particle scattering experiment are summarized as Rutherford's atom model. Okay, the Rutherford atom model is nothing but the results of alpha particle scattering experiment by a thin gold foil. Right. And Rutherford atom model help us to find or to calculate the diameter of the nucleus next to the size of the atom. Diameter of the nucleus and size of the atom. The diameter of the, how can you calculate the diameter of the nucleus? Simple, by using the distance of the closest approach formula. Okay, we know that the distance of closest approach formula R naught is equal to 2 Z E square divided by 4 pi epsilon naught, okay, into EK. So by using this relation, we can calculate the distance of the closest approach. The distance of the closest approach value is almost equal to the diameter of the nucleus. If you know the diameter of the nucleus, then we can calculate the diameter of an atom. The diameter of an atom is of the order of 10 power minus 10 meter. Diameter of an atom or radius of the atom is of the order of 10 power minus 10 meter, and the diameter of the nucleus is 10 power minus 14 meter to 10 power minus 15 meter. So depending upon the nature of the nucleus, the diameter value is vary from 10 power minus 14 meter to 10 power minus 15 meter. Right. If you know the diameter of the nucleus, then we can calculate the size of an atom. Size means volume of the atom. Okay, volume of the atom V is equal to 4 by 3 pi R cube, where R is the radius of the atom. Radius of the atom. So from this equation we can calculate what is the volume of the atom. So volume of the atom or size of the atom. So the Rutherford's atom model help us to find the size of the atom and as well as the diameter of the nucleus. Diameter of the nucleus. Right. Even though Rutherford atom model gives some useful results, however, this atom model has some drawbacks. Okay. So some drawbacks are listed out in our book. So first drawback, this atom model could not explain the distribution and arrangement of electrons in an atom. Right? The first drawback in the Rutherford's atom model is that it could not account for the distribution and arrangement of electrons in an atom. Arrangement of electrons in an atom. Right? And the second one, this atom model fails to explain the stability of the atom. Fails to explain the stability of the atom. Right? According to classical electrodynamics, the accelerated electric charges radiates electromagnetic spectrum, or whenever the electric charges accelerates, electromagnetic radiation is emitted. Electromagnetic radiation is emitted. According to Rutherford, the electrons in an atom revolve around the nucleus in circular orbit. So the electrons accelerates inside the atom. So when the electrons accelerate inside the atom, they must emit electromagnetic radiation. They must emit electromagnetic radiation, right? So inside the atom, the electrons, so this is nucleus, the electron revolves around the nucleus in circular orbit. Okay, the electron accelerates because the direction of velocity of the electron at every instant changes, so the electron gets accelerated. According to classical electromagnetic theory, all the accelerated electric charges must radiate electromagnetic radiation. Here the electron being a charged particle, okay, when it is accelerated inside the atom, so they must emit electromagnetic radiation. They must emit electromagnetic radiation, right? When the electron emits electromagnetic radiation, the energy of the electron is gradually decreases. The energy of the electron is gradually decreases. So it does not follow the same path. Instead, the electron is moves along the spiral path, and it must spiral down into the nucleus, right? So when the electron accelerates inside the atom, it emits electromagnetic radiation. When the electron emits electromagnetic radiation, its energy is decreases. Due to this, the electron is spiral towards the nucleus, and it must fall inside the nucleus. Okay, that is the radius of the circular path is gradually decreasing. The radius of the circular path is gradually decreases, and the electron must be spiral down into the nucleus. Must be spiral down into the nucleus. So the atoms becomes disintegrate. The atoms becomes disintegrate. So that is why an atom, okay, cannot be stable. Atom cannot be stable. Right? So this was suggested by Rutherford. The first drawback, the atom model, Rutherford atom model could not explain the distribution and arrangement of electron inside the atom. Okay, it could not explain the distribution and arrangement of electrons inside the atom. So this is first drawback. And the second drawback, atom cannot be stable. So Rutherford was suggested that atom cannot be stable. Why? Because when the electron is accelerated inside the atom, it must emits electromagnetic radiation. So its energy is decreases. Okay, so therefore the electron is spiral down into the nucleus. So the atoms becomes disintegrate. So the atom cannot be stable. Atoms cannot be stable. But it was experimentally found that most of the atoms are highly stable. Most of the atoms are highly stable. It is experimentally proved one. But according to Rutherford, atom cannot be stable. So this is one of the main drawback in Rutherford's atom model, right? And the third drawback, this atom model was suggested that the atom emits continuous emission spectrum of all the possible wavelengths. Okay, according to Rutherford's atom model, atom emits continuous emission spectrum of all the possible wavelengths. Continuous emission spectrum of all the possible wavelengths. Here, when the electron is moving along this path, it emits one electromagnetic radiation. Okay, now its energy becomes decreases. Then the electron follows this path. Again, another electromagnetic radiation is emitted. Okay, again its energy is decreases. Then it follows this path. Again the electromagnetic radiation is emitted. So the atom emits continuous emission spectrum of all the possible wavelengths. Continuous emission spectrum of all the possible wavelengths. But it was experimentally found that atom can emit line emission spectrum of a particular wavelength. Line emission spectrum of particular wavelength. So according to Rutherford atom model, atom emits continuous emission spectrum. Continuous emission spectrum. Second, this atom model, it could not account for distribution and arrangement of electrons in an atom. Okay, it could not explain how the electrons are distributed or arranged inside the atom. So this is the first drawback of Rutherford's atom model. Second, this atom model was suggested that an atom cannot be stable, but experimentally found that most of the atoms are highly stable. Third one, atom emits a continuous emission spectrum of all the possible wavelengths, but it was experimentally found that an atom can emit line spectrum of a particular wavelength. So these are the drawbacks of Rutherford's atom model, right? Okay, so far we discussed about J.J. Thomson's atom model, alpha particle scattering experiment, distance of closest approach, impact parameter, and the last one, drawbacks of Rutherford's atom model, right? So dear students, just you go through all this topic. If you have any doubt, you call me or send messages to my WhatsApp number. Thank you students, we will see you in the next class.